In this lecture, you will learn about hydrogen bonding, such as types of hydrogen bonding, properties of hydrogen bonding, and applications of hydrogen bonding with examples. The electrostatic interaction between a strongly electronegative atom and a partially positively charged hydrogen atom is called hydrogen bonding. The strong electronegative elements are mostly nitrogen, oxygen, fluorine, and chlorine. Two molecules involved in hydrogen bonding may be the same or different. Exceptionally low acidic strength of HF molecule as compared to HCl, HBr, and high is due to strong hydrogen bonding. Ammonia and hydrogen fluoride can form only one hydrogen bond due to the presence of only one utilizable lone pair of electrons and one utilizable hydrogen atom respectively. Water can form two hydrogen bonds as it has two utilizable hydrogen atoms and utilizable lone pairs on the oxygen atoms. The hydrogen bond between HF and ammonia molecules are represented as following. Some elements other than nitrogen, oxygen and fluorine are also involved in hydrogen bonding. For example, in chloroform, the three chlorine atoms make the carbon atom highly partial positively charged, which in turn makes the hydrogen atom also highly partial positively charged. This hydrogen atom can now form hydrogen bond with strong electronegative atom of other molecules such as oxygen atom of acetone as shown in the pic. The hydrogen bond is longer than a normal covalent bond. The hydrogen bond is stronger than dipole-dipole interaction but weaker than the normal covalent bond. It is generally 20 times weaker than a covalent bond. The hydrogen bond is a directional bond. Hydrogen bond results in the formation of long chains and a network of molecules. Hydrogen bond help in many approaches, and let's discuss these one by one. HF is a weaker acid than HCl, HBr, and hydrogen iodide. In HF molecules are hydrogen bonded in a zigzag manner. Hydrogen is in a trap between two fluorine atoms as shown in the figure. Therefore HF cannot easily donate a proton easily, who say it is a weak acid. In covalent hydrides of group 4A to 7A, hydrogen bonding effects are very clear. Consider the graph for boiling point of covalent hydride plotted against their period number. The boiling point of hydrides of group 4A are lowest among all covalent hydride. It is because elements of group 4A are least electronegative, therefore they have weakest intermolecular forces and are all covalent hydrides. For example, CH4 has lowest boiling point because it is a very small molecule and it has least polarizability. The boiling point of NH3, HF, and H2O are highest in their respective series. It is because these hydrides have strongest electronegativity elements such as nitrogen, fluorine and oxygen, which form hydrogen bonding among their own molecules. Therefore their boiling points are high. H2O has high boiling point than HF, although fluorine is more electronegative than oxygen. It is because chlorine atoms can make only one hydrogen bond per molecule due to the presence of one hydrogen atom, while H2O can form two hydrogen bonds per molecule because it has two hydrogen atoms and two lone pairs of electrons. Due to strong hydrogen bonding in H2O, its boiling point is greater than HF. Both H2O and ethyl alcohol are highly miscible with each other. Substances which can form H bond with each other are highly soluble in each other. Since both H2O and ethyl alcohol can form hydrogen bonding with each other, therefore, these are miscible with each other in all proportions. However, larger alcohols are not soluble in water due to nonpolar nature of bigger hydrocarbon chain in them. Similarly, small carboxylic acids are also soluble in water. Soaps and detergents are made up of long nonpolar hydrocarbons, alkyl or benzyl, and a polar anion head. In water, the head is stabilized by making H bond with water, while the nonpolar tail remains outside water because it is not soluble in water. Therefore, hydrogen bonding helps in cleansing action. Hydrogen bonding is very important in living organisms. Large protein molecules in living organisms are stabilized due to hydrogen bonding. Many fibrous proteins such as horn, nail, skin, feather, hair etc. are composed of long chains of amino acids. These chains are coiled around each other and form a spiral structure. This spiral is called helix. Such helix may either be right-handed or left-handed. In right-handed helix, groups like NH and C double bond O are vertically adjacent to one another and these form hydrogen bonds. These hydrogen bonds link one spiral to the other. The adhesive nature of certain paints and dyes is also due to hydrogen bonding with the surfaces. Similarly, sticky action of glue and honey is also due to hydrogen bonding. Food materials such as carbohydrates such as glucose, fructose and sucrose are also stabilized due to hydrogen bonding. All these contains hydroxyl group which produce hydrogen bonding. Water has a tetrahedral electronic structure. Ice floats on water in liquid when water molecules form a temporary hydrogen bond with each other. It is due to the movement of molecules, bonds are broken and reformed. Therefore, there is less irregularity and less free space. However, when the temperature of water is lowered below 40 degrees centigrade, its molecules become regular and form permanent hydrogen bond. So empty spaces are developed in between the molecules and their volume increases. This is the reason that ice occupies 9% more space than liquid water. Thus the density of ice becomes less than water. Hence it floats over water. For more such videos, kindly subscribe our channel and visit the article link in description.